Welcome to this lecture in this new series of lectures in group theory. Today we'll be looking at Euclid's theorem, and let us recall briefly what we have done so far. So last time we defined the notion of greatest common divisor. So if a and b are two integers, not both of them are 0, then we say that d, an integer d, non-zero, is a common divisor of a and b if it divides both of them. And the greatest common divisor of a and b is nothing but the maximum amongst all the common divisors. So you collect all the common divisors of a and b and take the greatest one. Greatest one exists because you cannot have the common divisor exceeding the magnitude of both a and b. So the maximum obviously exists. Alright, and lastly we saw a theorem which we won't use today. I said incorrectly that we'll be using this in this lecture. We'll be using this in the next lecture. So it said that if a is equal to bq plus r, where a and b are two integers, not both 0, then gcd of a comma b is gcd of b comma r. The notation was a little bit different, but this was the content. Anyway, so let's see today's problems. So there's only one problem, and this I should have given the last time, but I'm giving it now. Okay, and here is the main theorem that we want to discuss. So suppose we have two integers a and b, again not both 0, and d is their greatest common divisor. Then the theorem says that you can find integers x and y such that d can be written in this fashion. So in words it says that the greatest common divisor of two integers can be written as an integer linear combination of the two integers, if that makes sense. Alright, so let's prove this, and this is of course a non-trivial statement, but the proof is also quite interesting, but not very long, and one should be sensitive to what's going on, and we'll give another proof in the next lecture. Alright, so let S be the set of all possible linear combinations that you can form out of A and B, integer linear combinations, but we will collect only the positive ones. So amongst these linear combinations, there of course you can create negative ones here, but we will collect only the positive ones, and this set is non-empty. S is non-empty because a times a plus b times b equals a square plus b square is in S. And since not both a and b are 0, this is a positive number, and therefore this is in S, and S is non-empty. So we have that. And let, by the well ordering principle, we can choose the smallest element here. So let d be the smallest element in S. And we claim, we will show that d is equal to the GCD of A and B. Right. So since d is in S, we can choose x0 and y0 integers such that d is ax0 plus by0. Okay, and now we want to show that d divides a and d divides b. Right, I mean, at the very least we need to show that, because if d is supposed to be the GCD of a and b, then it better divide both a and b. So our first aim would be to show that d divides a and d divides b. So okay, so towards that, let a equals dq plus r, where this is the case, and this we can do by division with the remainder theorem. So this implies that a equals ax0 plus by0 times q plus r, where r is, again, we need to remember this. Alright, so if you do basic algebra, you will get this is equal to a times 1 minus qx0 plus b into minus y naught, or let me write qy naught. This is equal to r. Okay. So if r is positive, then r is an s. Why is that? Because this is an integer and that is an integer. And if r is positive, then this thing is of course, well, where is, yeah, so it lies here. But if r is positive, then it lies here and hence in S. So if r is positive, then r lies in S. But this is a contradiction. Contradiction to what? This is a contradiction to the fact that r is smaller than d. D was the smallest integer, smallest thing in S. So since d was the smallest thing in S, nothing else can be smaller than d, which is also in S. So if r is positive, then r is something smaller than d and also in S, and that is a contradiction. Contradicts the minimality of d. So therefore, we conclude that r cannot be positive. Thus, r is not greater than 0, and the only possibility for r then is r is actually 0, and this implies that d divides a. Why is that? If you look at this equation, r is 0, so a is equal to dq, and hence d divides a. Basically, remainder is 0. When you do this process, you find the remainder is 0 and hence d divides a. Similarly, d divides b. Okay? So we get, so without writing any extra line, we get d divides b also with a very similar logic. So therefore, d is a common divisor of both a and b, and thus d is at most the GCD of a and b. So this much is clear. I mean, yes, it is a common divisor, so that much is clear. And now, GCD of a comma b divides every element of S. Why is that? GCD of a comma b divides a, and GCD of a comma b divides b. So it divides this for each x and y, and hence it divides every element in S. So in particular, GCD of a comma b divides d, and hence GCD a comma b is less than equal to d, because d is a positive integer. And if you just combine star and double star, so by star and double star, we are done. And this finishes the proof because d is already in this form. D is an element of S, and everything in S is of this form. So we showed that G is equal to GCD of a comma b, and that's it. So this is Euclid's theorem. A very nice and very important theorem. Okay. So let us look at a simple corollary of it. So this should be intuitively obvious, but let us state this formally. So let a and b be two integers, not both 0, and d be a common divisor of a and b. Then d divides the GCD of a and b. So So of course it is at most GCD of A and B. That's just by definition of the greatest common divisor. But we are able to say more, that it divides the GCD of A and B. So here is the proof. Let x and y in Z be such that GCD of A comma B. This is I'm just using Euclid's theorem. So by Euclid's theorem we can find such integers x and y. And any common divisor of A and B will divide the right hand side. Right, it divides A and it divides B, and hence it divides this guy, and therefore it divides GCD of A comma B. So without writing much, I will just say D divides the GCD of A comma B. And that's it. That's a very nice proof. Okay, so this is all for this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.